Welcome to our Wednesday afternoon seminar. We're very pleased to have Eva Stavrov-Allen from Lewis and Clark College telling us about representing relativistic objects as aggregates of point sources.
So I want to thank everybody for interest in my work and thank the organizers for giving me a chance to present it. So let me begin with, why is it not working now? Interesting. Oh, it is. It's just slow. Okay, there we go. Let me start with a little bit of kind of philosophical framing of how this all fits together. So I think that a lot of personal impression that a lot of contemporary science and contemporary thought is kind of reductionist, maybe in flavor, in that a lot of the phenomena are explained in terms of aggregates of particles or units. And certainly that's clear if you want to think chemistry or something like that. And certainly there's this whole atomism idea that has a 2,500-year history, and it permeated a lot of Western thought. But if you look through the philosophy books, I guess atomism is contrasted with this other theory that doesn't have a consistent name maybe, but some authors use the word divisionism. And I guess there was this whole discussion of whether something can be infinitely dividable, or do you have to stop somewhere and then you stop somewhere and that's an atom. And I guess there's this whole thing about, on one hand, atomism, on the other hand, divisionism, but calculus somehow had served as an example, maybe more in the divisionism camp, because you end up talking about infinitesimals, which are results of infinite division, I guess. But for me, all of this is a little bit of, and granted, I failed philosophy in college, so I don't know if you should listen to me, but it all feels a little bit like splitting hairs, because at the end of the day in calculus, we are talking about aggregates, except that this time around, it's aggregates of infinitesimals. And, you know, you do your superposition / summation / Riemann sum, and then you take the limit and then you integrate. But at the end of the day, it's still integration or thinking in terms of aggregates. So that's me as a calculus teacher. I guess somebody who's more interested in understanding realistic objects, they might take a different perspective on this and say, well, look, realistic objects are made out of many, many small constituents, and keeping track of every single one of them is not going to happen. And so rather than, say, trying to understand a body of water by understanding what every single molecule is doing, employ continuous variables instead and make use of continuity and Euler equations, and then try to understand the behavior of a system through differential equations. And to get that kind of idea off the ground, you employ this idealized point object construction where you assign some kind of an averaged attribute to a point object, and that usually takes the form of a density. So an example would be mass density, where you have units of, for example, kilograms per meter squared or something like a meter cubed. But then you create, based on that mass density rho, you create mass element, so rho d vol, that would have the units of, say, kilogram or something like that. And then in order to find the aggregate, so the cumulative effect, you end up integrating all of those mass elements. And, you know, as a mathematician, I'd like to say that Riemann sum maybe approximates the integral, but I don't know. There's perhaps the wisdom in thinking the other way also. And thinking the other way would be that it's actually the integral that approximates what is perhaps more realistic, which is a Riemann sum. So how does all of this relate to relativity? So basically, I mean, this is all maybe simplified, but what molecule is to a body of water, a star is to galaxy, or a galaxy is to universe. And in a way, you can think of stars as being point objects. And their individual kind of length scale is negligible relative to the length scale of the universe as a whole. And any sort of inhomogeneities or lack of symmetry also are negligible from this like grand cosmological perspective. And so on one hand, I'm going to think of stars as being point objects. On the other hand, to describe them, maybe what I want is a model that has a great deal of symmetry, and somehow everything is concentrated at one single point. And if you've had experience with relativity, I'm alluding to Schwarzschild or Reissner-Nordstrom models. I won't talk about Reissner-Nordstrom much. I'm going to, for sake of simplicity, not introduce charge. So for all practical purposes for this talk, what I'm referring to is Schwarzschild solution. So as a summary, right, when you study things on cosmological scale, you're kind of effectively saying universe is a perfect fluid. And there's this correspondence between, for example, a star and a molecule of water or something like that. And then at the level of differential equations, the counterpart to continuity and Euler equations would be Einstein field equations for perfect fluid. And so this is a good point to kind of frame how my work fits into all of this. So there's this transition, which is taking the limit of a Riemann sum that takes me from mass elements to mass of like the macroscopic body as a whole. But what is not at least very well documented in the literature, at least that I understand, is how do you go from something like a Schwarzschild model of a point object to a perfect fluid solution of Einstein field equation? And basically the question is, what is playing the role of a Riemann sum and what kind of a limit should I be taking? And in a nutshell, the work that I've done points to the possibility that Riemann sum means what I will call Brill-Lindquist Riemann sum, and you'll hear about them a lot. And the type of limit involved is Gromov-Hausdorff or intrinsic flat. Finally, let me give credit where the credit is due. So all of this got started in a conversation that I had with Cristina Sermani many years ago at a conference in China. And then after that, I converted this into a whole bunch of little problems suitable for work with undergraduates at my college. And so these are some of their names. There were more people involved, I will say, but these are the 4 students whose work is at least up on archive, if not published formally. And also, I should express gratitude not just to Christina, but of course, Paul and Jim Eisenberg, who have been central in my relativity life, but also David Maxwell, who has pointed out one feature that is crucial for all of this to get off the ground. So that's the framing. The work that I have done is within the realm of initial value formulation, or rather initial data for general relativity. And so a couple of words about that. Universe, you can, I guess, view it as a 4-dimensional Lorentzian manifold, meaning, I suppose for every moment in time, you have spatial geometry. And in a sense, you're saying, okay, at this moment, the geometry is this particular Riemannian manifold. And then as time changes, so does the metric on this manifold. What would cause change? Well, the presence of matter that's around. And the Einstein field equation that I mentioned earlier basically relates the matter content to Ricci curvature of that 4-dimensional manifold. And at the end of the day, the Einstein field equations basically give you a second order nonlinear wave equation for the spatial geometry. However, being second order, the initial data that you need to have is not just the original geometry, so not just the metric G, but also its time derivative, so G dot. But G dot, time derivative, I mean, that's effectively the second fundamental form of the spatial slice as it sits inside of the Lorentzian manifold. So really, the initial data is consisting of the metric and the second fundamental form. But of course, there's Gauss-Kodazzi equations, and the metric and the second fundamental form can't just willy-nilly be anything that they want to be. They have to satisfy certain constraints, namely Gauss-Kodazzi equations. And to be fair, Einstein field equations are equivalent to this coupled system of second order evolution equations for G, where G and G dot satisfy the constraint equations. And I've written the constraint equations in almost full, I suppose, on this slide, but I will set the second fundamental form to 0, partly for simplicity. And that is then referred to as time symmetric initial data. And it's basically consisting only of metric G, and its scalar curvature is thus related to quote unquote energy density. And this is the equation at the bottom of the slide, and it says that the scalar curvature is equal to a certain multiple of energy density. But you can think of this, I suppose, as a prescribed scalar curvature problem. And at that stage, this whole story connects to geometric analysis. And if you have background in prescribed scalar curvature, this ansatz that's on this particular slide is not necessarily surprising. So I'm going to assume the underlying topology of a punctured R3, and I'm going to be seeking metrics that are conformally equivalent to the Euclidean metric on such a punctured R3. And I'm going to impose that the metric is asymptotically Euclidean, so that theta will have to, I will ask that theta goes to 1 at infinity. Now, given how scalar curvature behaves under conformal change of metric, the prescribed scalar curvature equation, if you will, becomes an elliptic problem for theta. And that has Laplacian in there. And in some ways, you could think of this as being a relativistic Poisson equation. And I'll speak about that a whole bunch more, but heads up, this theta that is going to be present in all of this work, the conformal factor theta, is in a sense relativistic counterpart to the gravitational potential as you learn it when you learn basic physics. And that's made very apparent in the example, vacuum example. So vacuum example means I'm going to let the Laplace theta be equal to 0. And I am also going to permit only one puncture, so only one pole, if you will. And when paired with the boundary condition of 1 at infinity, I will arrive at this kind of Green's function expression for theta, 1 plus m over 2r. And this m over 2r, you will maybe recognize it as being the expression for the gravitational potential for a body of mass m at the origin. Vice versa, if you think of this in terms of geometry and you look at the geometry given by this conformal factor 1 plus m over 2r, the appearance of that geometry is this hourglass shape. And there's 2 asymptotic ends, 1 at infinity and 1 at 0. And if you sit down and compute what the ADM mass is of each one of those asymptotic ends, you are indeed going to get that the ADM mass is m. And so I like to think of this particular example, which is the example of initial data for the Schwarzschild solution of Einstein field equations. I like to think of that as kind of illustrating how there's this intuitive correspondence maybe between theta and conformal factor theta and the gravitational potential. And then you can try, at least on some naive level, to do a superposition of gravitational potentials. That leads to this conformal factor with a summation in it. So MI here are understood as mass parameters for bodies located at PI. The resulting geometry has the appearance as in the middle of the slide. Of course, basically each PI will have an asymptotically Euclidean end associated to it. And then you can get into this whole business of trying to compute the ADM mass of various asymptotic ends. And what you will find is that the ADM mass of the asymptotic end that is represented by this sheet at the very top is the sum of the parameters MI. Kind of what you would expect, that the total mass is the sum of individual masses. So that kind of seems straightforward. But there are surprises with this. And the surprises are all well documented and explained in the paper by Brill-Lindquist in the from 1963. Which is why I refer to this as Brill-Lindquist initial data.
I see a hand up.
Sorry, can I ask you a question? I'm a bit confused. When you say it's asymptotically Euclidean, does it mean the manifold is not expanding, or is it static at the boundary, or?
What it means is that to a large degree, G is approximated by G Euclidean at infinity.
Okay, because I'm coming from the cosmological background, that's why I'm confused. Because when I put the bodies of masses inside and a perfect fluid, then I expect there to be the scale factor and the time evolution. So the spatial manifold to be expanding.
This is just initial data.
Yeah, this is
just initial data. Sorry. So it's not the. Okay.
Yeah, and I think that maybe there is something to kind of towards answering your or addressing your question, maybe address what would the answer be in the case of just Schwarzschild? And then, so the Schwarzschild is asymptotically Euclidean in a certain way. So what does that mean? And the answer would be the same for Brill-Lindquist.
Can I also ask a question?
Okay.
Can these masses also be negative, or do they have to be positive?
Positive. I only do positive.
And it wouldn't work if they're negative, or?
I didn't try, I should say.
Okay.
So I shouldn't say anything because I didn't look. Possible. I'm not saying no or yes. I don't feel confident answering because I didn't try. Is that good? Can I continue?
Yes, thanks.
Yes. Go.
Okay, so I was saying how this was addressed in the work by Brill-Lindquist from the 60s. And so what was nicely documented and explained there is that, let me go back actually for a second. If you go to these asymptotic ends at P1, P2, etc., and compute ADM mass there, you will not get the individual MIs. What you get is MI and then the contribution of what in effect are interaction terms between different bodies, one at PI and another one at PJ. And the discrepancy between the ADM mass of the big sheet at the top and the sum of the ADM masses of little individuals down at the bottom really does match the expression for interaction energy within that whole cluster of bodies, so to speak. And this maybe is a elegant way to like explain why ADM mass is not additive in any kind of straightforward sense, and why this quest for quasi-local mass is such an important and well investigated, I mean, deeply, people have invested a lot of energy into understanding what quasi-local mass means, and it's not easy exactly because of this. Here is a kind of a heuristic explanation of what is going on that I have used as a rhetorical argument with my undergraduates, because of course, talking to them about ADM mass is not easy, but this is pretty compelling. If you have two bodies of mass M1 and M2, on one level, you could say that the total mass is the sum of M1 and M2. But to the extent to which you want to embrace relativity, you have to also maybe take into account the equivalence between mass and energy. And so you have to throw in the correction term, which is the interaction energy between M1 and M2. And so the total mass of the system, or as Brill-Lindquist would call it, bare mass of the system, maybe, would be the sum of M1 and M2. That would be the effective mass, and then also the interaction term. And you can extend this to any number of bodies. Thus these big sums at the bottom of the slide. What is here is basically the same expression, though this time around written with a language of Dirac delta functions, saying that these are matter distributions that are concentrated at points, pi. And this is a cheat, but at least it looks right at first glance. It's actually not fully right, and you're going to see exactly what's happening in a minute. But at least it looks factorable into...
could I interrupt?
Yes.
One thing that looks not right is the interaction energy is negative potential energy, not positive potential energy.
There are minus signs are off.
Okay.
A lot of this. Yes.
Yeah. Thanks.
Yeah. And it's not a type. It's just everything that's on the slides is actually consistent, but from the get-go, there's some minus signs discrepancies. In any case, so there's an issue with the minus signs, perhaps, but there's also another algebraic issue in here that's actually far more deep, I would say, and that. But at least at first glance, it looks like the total mass actually factors into a product of what earlier on I described as the gravitational potential theta, up to signs, and this term that is the plus of theta. So really, this relativistic Poisson equation that I mentioned earlier briefly takes the format of theta Laplace theta equaling the mass energy density. So this is kind of an informal way of arriving at that equation, but I'll show you a more geometric way of arriving at that equation. I'll go back to the constraint equations I mentioned earlier. And I mentioned earlier how the constraint equations boil down to, in the framework that I'm using, to one prescribed scalar curvature equation. R of G is equal to 16 pi rho. So that's in the middle of this slide. But so rho would be given in the units of its density, right? So metaphorically speaking, it's given in the units of kilogram per meter cubed. But what meter means depends on the metric. And there's a little bit of circular logic in here if you think about it. On one hand, you can think of this equation as, okay, you prescribe matter and metric is created in response to the matter present. But prescribing the matter in kilograms per meter cubed only to figure out in hindsight what meter meant in the first place is a little bit odd, if not circular. And it was David Maxwell who pointed this out to me, and it was really from this point on that like this whole set of projects managed to like blossom. And what he taught me is that rather than prescribing scalar curvature, so rho, I should really be prescribing the metaphorical kilograms, which is rho times d volume. So basically, the matter should be prescribed as a 3 form. And this scalar curvature equation is really the constraint that scalar curvature times the volume form is equal to 16 pi omega. Omega this time around having units of kilograms. If you employ the ansatz that the G is conformally equivalent to the Euclidean metric, this expression for scalar curvature times the volume form really does produce the theta Laplace theta that I showed you kind of from heuristic reasons, kind of arising earlier. And so the relativistic Poisson problem for me will mean this equation theta Laplace theta times the volume form equals negative 2 pi omega. And I really get to think this time of like, you give me the mass distribution omega, and I can find such a theta always. If you're well steeped in the prescribed scalar curvature stories, this might come as a surprise, but I think that the crucial difference is in this exponent on theta. So when I write the equation in maybe the form that is more familiar, more looking like a Yamabe equation or something like this, instead of getting the exponent of theta to the 5th, I get the exponent of theta to the negative 1st. And having the exponent of -1 really works out in my favor. So yes, it's a prescribed scalar curvature, but no, not really, because of the difference in the exponent. So here's the basic framework in summary. So I'm thinking matter will be prescribed in the form format. So it'll be a 3 form on punctured R3. I will give myself the constraint equation, which becomes a relativistic Poisson problem. I can always solve it. And in response, I get some kind of a geometry with some kind of a gravitational well, perhaps. And another thing to keep in mind maybe is that this relativistic Poisson problem decomposes omega into its effective mass component and the interaction energy component. Okay. So now moving towards what I could mean by point source and going into the idea of point source a little deeper. On one hand, I could think of point source as being the setting where you take the matter distribution to be a multiple of Dirac delta. On the other hand, I could think of point source as being that Schwarzschild geometry I discussed earlier. And maybe those two things, maybe those 2 bullet points give me the same thing, maybe not. We're to discuss this. But let me say that whatever the point source may or may not be, it should be such that there's some kind of a mechanism of seeing a point source as a limit of matter distributions that are becoming more and more concentrated at a single point. And there should be some kind of a mechanism of seeing a continuous matter distribution as an aggregate of point source configurations. And so with my student Noah Benjamin, I set out to, it was kind of his idea, I should say. I didn't expect that this was going anywhere, I have to be honest, but it was his idea to pursue what happens if omega is set to a multiple of the Dirac delta function. And I'm going to think of a multiple of Dirac delta function in terms of this picture on the bottom of the slide. So there's some kind of a prefabricated matter distribution omega on a unit ball. And I'm going to place it into R3 by means of these dilations. So it's kind of a push forward, if you will, of a 3 form into R3. And it's these parameters Rn are becoming smaller and smaller, going down to 0. And in effect, what happens is that the matter distribution omega becomes more and more concentrated at a single point. But the total integral is the same. So this is really kind of a sequential way of looking at the multiple of Dirac delta. And the sequential nature of this approach translates into a study of a family of relativistic Poisson problems. And then the goal would be to investigate the limit behavior of the geometries. And the first surprise happened pretty quickly, and that was that in the limit, you actually don't recover the Schwarzschild solution. And the picture of the limit is on the bottom of the slide. So as the matter distribution becomes more and more like Dirac delta, this gravitational well becomes more and more like a bubble, and the asymptotically Euclidean end becomes more like a just flat sheet. I understand this is actually 3D, so it should be Euclidean space with a 3-dimensional sphere attached at one single point. So it's literally like, I mean, reduce it 1 dimension, so it's a sheet with a sphere attached at a point. I can talk about this metric on a sphere in a second more, but again, some of this was known. The top sheet part, that was known. That was in the work of Arnaud, Desser, and Misner back in the 60s when they first formulated what is now known as ADM mass. But the bubble part on the bottom, I didn't see that. I didn't know about that. I didn't see that in the literature. But that was, for the first time, really came to my mind and my awareness through work with my student, Noah Benjamin. And that work has appeared in GRG since. And I have to say that at that point, I found myself rethinking this idea that point sources need to be described by Dirac delta, or rather that there might be other models for point sources. And I suppose this is how I see my talk fit into the theme of low regularity in physics and geometry. What we did past this point is kind of turn the problem upside down and started studying what happens. I mean, what kind of omega would be corresponding to Schwarzschild body in the first place? In other words, if I were to, so to speak, plug in the conformal factor for the Schwarzschild body, what kind of omega do I get on the right-hand side? And the computation is at the first display of this slide, and you'll see an M delta showing up like you'd expect, but also you end up getting a, in effect, interaction term, M squared delta over 2R. On one hand, that's nonsense because delta over R, I don't know what that represents. There's no kind of functional analysis way for me to think about it. On the other hand, I'm not blind. And I mean, I see that this is a continuous version of the expression for the ADM mass of the Brill-Lindquist metrics at those sources PI. So I see that this, schematically at least, this expression has a precedent. And we were looking at this and realized that the reason for that surprising result that I mentioned earlier of a sheet with a bubble underneath is that this expression for omega Schwarzschild is dominated by this self-interaction term, if you will, which is M squared delta over 2R. And maybe this is, working with undergraduates. I mean, they don't know any better, right? And so I couldn't say no to studying the possibility that maybe there's a point source model that's based on delta over R rather than delta itself. And so what we did is, once again, we looked at a prefabricated, so to speak, distribution omega, and we shoved it into the space R3 by means of dilations. So there's a whole bunch of push forwards, but appropriately scaled pushed forwards. And so in the middle of this slide, you're going to see that the push forward of omega without any scaling is like delta. But if you multiply that push forward by n, it will scale like delta over R. So in a sense, if I may, I'm going back to this picture. So I'm taking a prefabricated omega, I'm pushing it forward into R3, but then I'm also elongating it even more by a factor that's reciprocal to Rn. So I'm understanding that as delta over R. And it's a sequential approach to delta over R. And so the task was then to study the limit geometries with the, so I guess I get a sequence of relativistic Poisson problems. And I'd like to study the behavior of the sequence of geometries, and specifically, do they have the limit that I'm hoping they would have, which is the Schwarzschild metric. This work is published already. And if you look at it, it's dancing around a lot of, or dancing around this relativistic Poisson problem, but the boundary condition is set to 0. So it's not, I mean, I don't know if I should be using the phrase relativistic Poisson problem because the boundary condition is different. And the key result, honestly, in that whole paper is the existence of a solution of such an equation. And it's the solution of that equation that describes or defines the bubble that you saw on an earlier slide. But to be honest, in hindsight, now that I've done what I've done and some other students have looked into this, I'm realizing that we missed one point, and that is that perhaps this omega should have been normalized from the get-go. And what you see in the rest of the slide is how omega and theta behave upon scaling. And there is a way to always find the scaling factor C so that the integral of omega over theta is set to 1. So should you look into the paper that I've written with Noah Benjamin, you will see things written slightly differently, and there's something that was missed in there, and that was perhaps that omega should be normalized so that this integral is 1. So there's tons of integrals over there that really should have been kind of bypassed by this normalization. Now, it might feel like this is just algebra. Why am I bothering to mention this? It was interesting for me to notice that if you keep track of units throughout this business, and thank you, Christina, I actually mean this, like one of the things that I learned through working with Christina was that there's a lot to learn from paying attention to units, right? And when I focused on like, okay, so what are the units on omega naught and theta naught? And I realized they're 1 over kilograms. And that was really confusing to me until I realized that what it really means is that they need to be binded to mass. And ultimately, I was comforted by the realization that this omega naught that I mentioned earlier on the previous slide, having units of 1 over kilogram, it's really awaiting a parameter like mass squared. So it's awaiting a kilograms squared, much like the proverbial delta over R is. And so there's something comforting about this at the whole. Is the whole point, I suppose. So in a way, this omega naught that I'm mentioning is the delta over R, and it will be multiplied by m squared. So the result of now Benjamin and myself is that if you start with a normalized omega naught and you push it forward with these dilations into R3 and scale them in a way the delta over R scales, so appropriately scaled push forwards, multiply by m squared. So that's our model for m squared delta over R. So if you use that framework, then lo and behold, you really do get the picture that we were hoping from the get-go. So what's better is that this is actually extendable to several point sources. That work is on archive. I haven't submitted it yet. There's some complication, not having to do with math. Everything's fine in there. Long story. But the work is on archive. So it's now Benjamin, Will McDermott, and myself. So we extended this to a situation when there's multiple point sources located at pi, each one with an effective parameter mi. And then we had made like a straightforward, like simple most superposition you can possibly think of, except rather than having an mi as a constant, we did mi squared, thinking to ourselves, all we're doing is superpositioning sources of delta over R genre. So the expression for that is at the bottom of the page. Things to note. When I mentioned the relativistic Poisson problem earlier, the heuristic behind it, I was talking about the effective mass and the interaction energies, and there were a whole bunch of these mi, mj terms, you will recall. And there are no such terms in the expression for omega. So the only interaction terms that are present in omega are self-interaction terms. There are no mi, mj terms. And so at first glance, this shouldn't work at all, because it's somehow what is placed at pi doesn't see anything else. And yet, we really do get the convergence towards the straightforward superposition of gravitational potentials, as I described earlier when I talked about Brill-Lindquist metrics. And so this is highly unexpected because the Poisson problem is nonlinear, the one that we're studying. And yet, this is some kind of a superposition principle for the relativistic Poisson problem. So that was very surprising. And I think that out of all the work that I've done with students, that may be the one that kind of struck me the most, I will say. I did a whole bunch of continuum limits, which I don't believe I have time to talk about. I was afraid that this talk was too long, but so
right, you have about 6 minutes, I think.
I have 6 minutes. Okay.
Yeah.
Okay. So I will say that in work with another student, Tatiana Benko, I have also examined the extent to which the Brill-Lindquist metrics can be taken the limit of to produce a continuous matter distribution. So towards taking the continuum limit, let me start with a matter distribution omega. And I mentioned earlier how the relativistic Poisson problem decomposes omega into the interaction and the effective mass distribution part. And the effective mass distribution is the Laplace of theta, as is pointed out in this first equation on the right. So for a given matter distribution omega, I can find theta by means of the relativistic Poisson problem. And then Laplace theta up to some minus signs, factors of 2 pi, what have you, determines the effective mass distribution M. So once I have an effective mass distribution M, I can quite literally repeat the story that I tell undergraduates when I teach them Riemann sums. So if M is given over a box of sorts, I can divvy up the box into little miniature boxes, evaluate the function M at a point, center point, for example, within that sub box, and then form the Brill-Lindquist Riemann sum. So this goes in absolute parallel to Riemann sums. Of course, the goal is to look at what happens in the limit as n goes to infinity. So as the subdivisions are becoming finer and finer. And that maybe looks promising at first when you look at algebraic expressions. But of course, once you realize that the Brill-Lindquist metrics look this way, that becomes less obvious. And so what hope into this working one has to be rooted in the observation that Riemann sum algebra, at least on a formulas level, right, converges to the function theta of x defined by this, in effect, Green's representation formula expression. And if you look at, for example, the Hamiltonian constraint satisfied by the metric theta to the 4th G Euclidean, which is at the very bottom of my page, you will find out that the kind of limit, hopeful limit of these geometries is nothing but a constraint equation for a dust cloud. So hope that things would work will be rooted in this, yet you look at the previous picture, I don't know about this whole thing. So whatever convergence it is, it's not going to be an easy convergence. So considerations of scalar curvature will tell you pretty quickly it's not a C2 convergence. And even if you look at where you might have C0 or C1 convergence, the sets on which you have them are very kind of Cantoresque in appearance. And this is all to say that at the end of the day, you kind of have no choice but examine convergence that is based on techniques from metric geometry and geometric measure theory. And so I'll skip a couple of slides. Unfortunately, I don't have the time for that, but here is the ultimate result that I have with my student. I do indeed get the convergence if I employ a Gromov-Hausdorff and the intrinsic flat limit from going from Brill-Lindquist Riemann sums towards the dust cloud. If you go and look into this paper, you will find out that the bulk of it is dedicated to identifying where the minimal surfaces / horizons are for the individual bodies at PI. That's more than half of the paper is literally computations of that. There's also a lot of gymnastics in there because everything I've shown you today, it assumes no charge present. If you were to do this in the charge context with Reissner-Nordstrom metrics, this will become a whole lot more complicated. And I will say that Gromov-Hausdorff limit is not going to do it. And you have to do intrinsic flat limit in that situation. So it just happens to be nice. The Gromov-Hausdorff thing works in the situations when there's no charge. But otherwise, you do want to use the intrinsic flat limit, and the whole story becomes a whole lot more technical.
Okay, maybe summing up now.
Yeah. So, in summary, the biggest result that I wanted to show today was that despite the nonlinearity of the relativistic Poisson problem, I did manage in work with my students establish some kind of a nonlinear superposition principle for it. And it opened the door to a possibility that maybe the right model for point sources is not given by the Dirac delta, but delta over R. But I'm going to make a speculation here of sorts. I mean, what I've shown you doesn't fit within any sort of functional analysis framework. And I want to speculate that actually that can be done. And I'd love to do that work, but then again, I'm also waiting for the right student to do it with me. So I think I'll leave it at that.
Thank you very much. So we're a little over time.